Hello, everybody. Before we talk about gas laws, we need to talk about pressure. We need to understand what pressure means because it's one of the characteristics of gases we're going to need to use when we do calculations. So we'll begin with some kind of definition. So pressure is force per unit area. And one kind of pressure that we all experience all the time is air pressure. And air pressure is caused by all of the gas particles that are around our planet being moved in a downward motion by gravitational force. And so one way of thinking about air pressure is that it's the weight of the air above you. And when we think about the weight of something, we think about pounds, which has the abbreviation LB. And for area, we could express area as square inches. So pounds per inches squared, pounds per inches squared. And if you listen to me say that, pounds per square inch, then you can see why this is sometimes called PSI, pounds per square inch. So atmospheric pressure is 14.7 pounds per square inch. And what that means is that if you were to draw an inch on a surface that was at sea level, and then somehow you were able to draw some kind of column, some kind of tower that was exactly an inch square, all the way up to outer space, that tower would contain air which weighed 14.7 pounds. So here's the Earth, here's outer space, and here's this tower of air that weighs 14.7 pounds. So we call that particular pressure air pressure. At sea level. And if you think about it, it's not always going to be exactly 14.7. Air pressure changes, so that represents an average. So I would say 14.7 pounds, give or take. Now, when you drive a car, you fill up tires with air, and to figure out how much air you put into a car tire, you measure the pressure of the tire. And a typical pressure for a tire is about 30 psi. So that's for a tire. So let's see if I can remind you that that's a tire by drawing a little car here. Okay, there's my car. And there is the wheels. And we have 30 pounds per square inch for those tires. Now, this is higher than 14.7 pounds per square inch. And that makes sense because we want the elastic tires to be firm. We want them to be able to absorb shocks. So we put air inside them that's at a higher pressure than the atmospheric pressure. And this creates a force that pushes outward on the tire and keeps it nice and firm. If you're talking about a bicycle, sometimes a bicycle is inflated up to like 90 psi or even higher. Those are really thin tires, and they have to be under very high pressure in order to stay firm when you're riding a bicycle. So that's one way of thinking about pressure, force per unit area. But pressure comes up in so many different discussions. It comes up in discussions of weather, like in meteorology. It comes up in discussions of chemistry when we talk about ideal gas laws. It comes up in discussions of physics. It comes up in discussions of mechanics, pneumatics, engineering, and on and on and on. And every single area of science seems to have picked out or attached itself to its own favorite units. So pressure has so many different units, and I'll go through a few of them that you'll be seeing more often. One unit that's used is the atmosphere. So 1 atmosphere, by definition, is the pressure of the atmosphere at sea level. And again, we have to standardize that as an average value. It's not going to be exactly the same everywhere you measure it all the time. Otherwise, we wouldn't have weather. I mean, weather is caused by high pressures and low pressures and storms and so on. So 1 atmosphere is this hypothetical average pressure at sea level. But to standardize it, we set that equal to 14.7 pounds per square inch. So we know that 1 atmosphere of pressure is equal to 14.7 pounds per square inch. And if we wanted to convert from 1 unit of pressure to the other, we would just use this conversion factor. But there's more. The next unit of pressure that I want to discuss is the millimeters of mercury, and also called torr. So torr is short for Torricelli, and Torricelli invented the barometer. So let's think about that for a minute. So what he did was he had a big container, sort of like a dish, and into this dish he put a pool of mercury. Then he took a glass rod and he inverted it, and it was also filled with mercury. So it was filled with mercury. And there was almost a vacuum at the top of it. Not much air here, very little pressure, very little air. So we'll say very little air here. But the atmospheric pressure presses down on this pool of mercury and causes the mercury inside the tube to rise above the level of its bath. And then he calibrated it. So he measured the height in millimeters. And it turned out that it was 760 millimeters of mercury on average that turned out to be equal to 1 atmosphere pressure. So again, we have 1 atmosphere. We know it's equal to 14.7 pounds per square inch. And now we can add to that the 760 millimeters of mercury. But because we wanted to honor Torricelli for his invention, we also call this a torr, so 760 torr. Now it turns out though that if you're going to talk about height, here you're using millimeters, so that's a metric system, but you can also measure height in inches. And that's kind of confusing because we're no longer talking about a force per unit area unit. We're talking about a unit of length. But we understand that this unit of length is measuring a height of mercury in a barometer. So that led to the unit inches of mercury. And if you convert 760 millimeters to inches, you end up with 29.921. So 29.921 inches of mercury. It's important to not just say inches. That wouldn't make sense. That would be a length. You have to say inches of mercury so that it's understood that you're talking about a barometer and you're talking about the height of a barometer. Then we have another unit that is used in physics, and this unit is the kilopascal, and it's 101.325 kilopascals for atmospheric pressure. And then there's another unit called the bar, and the bar is related to the kilopascal. It's 1.01325. So the bar is very close to 1, and it's beginning to be used more and more often as a standard. But in our unit in chemistry, while we're studying gases, we will most often refer to pressure in the units of torr or atmospheres. These are the favorite units of the chemists, these two. And all the other units come up in other fields. You should at least take away from this discussion 2 things. First of all, many areas of science need to refer to pressure and discuss concepts of pressure. And they've all picked their favorite units, but pressure is pressure. It's the same thing, regardless of what units you put it in. And so it's important to have some flexibility. It's almost like speaking many languages. These are the many languages of discussing pressure. And it's very easy to convert from one to the other. It's very easy to just do a mathematical operation. So let me give you a couple of examples of that, and then we'll wrap this up. So for example, suppose that you were told that, well, I mean, you could look right now. I'm gonna do it. I'm gonna look on my phone and I'm gonna see what the current atmospheric pressure is right now. And so when I pull up my weather app and I look, it tells me that right now in Chicago, it's 29.81 inches of mercury. And suppose I would like to know what that translates into in terms of torr. How would I do that? Well, you just multiply by 760 torr divided by 29.921 inches of mercury. And just like we've always seen with unit analysis, the inches of mercury cancel out and we're left with the units torr. So let me grab a calculator and see what that turns out to be. So 29.81 times 760, and then divide it by 29.921. And I find out that that is 757 torr. So very close to 760, slightly lower than 760. And I'm 500 feet above sea level in Chicago, so that seems like we're at about the right spot. All right, that's all for now.